This is Statistics 243 at Berkeley for Friday, September 27th or 26th, the 12th class of the semester. Okay, so for today I want to keep talking about computational efficiency and strategies for improving the efficiency of our code. And we left off last time and we had sort of finished up talking about pre-allocation, even though in R you don't need to pre-allocate. You don't need to explicitly request memory, that it's still a good idea to do it rather than creating objects that you incrementally add onto. So as we were finishing up, Greta asked a good question of me just in front here after the end of class of what would you do if you don't know how long the size of the vector is that you need until you actually start running the code. So did you have an example in mind of when that might happen?
Yeah, so like if you're, like for example in problem set 2, when you don't know how big the original data set is that you're reading in, and you're trying to keep count of something that's in that data. So if you're trying to create a vector of all of those new objects that you're like looking for or something like that.
Right. I mean, one example might be if you were, say, if you were processing a bunch of data in chunks, and you were trying to count up the number of each word, for example. But in every chunk, you might get some new words that you hadn't seen before, and you wouldn't know how many unique words there were. So that comes up a lot. So did people have any thoughts of how to handle that particular problem?
Create an excessively large array at the start.
Okay, so yeah, sort of the inelegant approach would be make something that you think will be big enough in hopes that it'll be big enough, and then start filling that in. Okay, so what else? Other ideas? Yeah, Julie?
Smaller fixed-size blocks, so like wheel blocks of a certain length, and then those. I don't know if it's the same.
Yeah, that's actually not a bad idea. Like there's still some inefficiency there if every time you tack a new block on, that it might take some time, but it's going to be better than tacking on one at a time. On the other hand, how would you know how many blocks to create?
That you would.
Okay.
You could make a fixed block.
Okay, so you're saying create one block at the start, and then if you get to the end of that, create another block and tack on, something like that.
And you could maybe do a parallel.
Chris?
Whenever you reallocate, you multiply the size by some number like 10 or 100, so that way it scales.
Oh, that's a nice idea. Right, so if you don't have any idea coming in, like even what magnitude of object you're going to need, you wouldn't want to then start with 10 and then keep adding on 10 at a time. And so if you get to the end of 10 pretty quickly, that might be a sign the next one should be 100 long and then 1,000 long, something like that. Any other ideas? These are all good thoughts. Yeah, Eugene?
You can sort of implement the linked list kind of structure. If you use a list of agencies, when you fill one up, you can make another one add to the list. Keep filling it up, and then
Yeah, I guess that's sort of like Julie's idea of doing it in blocks.
you need to reallocate all the time. That's the thing.
Well, you would or you wouldn't?
You wouldn't. You're having an unlimited known data set, right? The big part is copying smaller arrays, the larger arrays
Right.
you reallocate.
Right.
You have a linked list structure, you're putting it to.
Well, but R doesn't have, I mean, if we think of so you're thinking of creating an empty list and then filling in pieces into that list?
Well, have like a list of pointers.
Yeah, but there are no pointers. I wonder if you create an empty list and then you have an initial vector and you put that vector in as the first element of the list, and then you get to the end of that, and instead of tacking the next vector onto the first vector, you just put it in as the second position in the list. I guess that would involve copying the list every time you do that, but if you're not doing it too many times, it might not be too bad. Other thoughts, Scott? No? Okay. All right, so there are some things you can do. All of these, so all of those ideas I think are reasonable to think about. None of them are maybe particularly elegant, but they would get the job done, and you're sort of working in the land of approximation here. Okay, yeah.
For example, in Fortran, if you don't declare a variable at the beginning, it will flag an error when you compile. In VBA, which is more than interpret languages, you can set option explicit to do the same thing. That way, if you're typing code, you misspell a variable, you won't create a new one, it just flags it.
Yeah, I
Is there
don't.
an option like that that.
I don't know of any way to do something like that in R.
Yeah, Python is the same problem.
Okay, so let's see. So let's turn back to the unit here. So the next little section was on vectorized calculations. I don't think I'm going to say too much about this because in essence this has already come up a bunch, but obviously if we're working in R, we do want to do vectorized calculations, and there's some examples here of just seeing how much faster it is to do a vectorized calculation than a for loop, for example. One of the things I emphasized in problem set 3 was when you can to make your own functions vectorized so that they take as an input a vector and then they operate in a vectorized way and return as an output a vector. So some of this is you using a vectorized function that R provides to you, but some of this is when you're using R, if you can, write your functions to operate in that way as well. Yeah, Kelly?
Is it possible that a vectorized function might, I mean, I'm sure it's possible, might not be optimal for something like, say, if you want to, it kind of goes back to one of the examples you had in class last time, where instead of appending, you pre-allocated a blank list of a certain length, and then you use the for loop to fill in that list instead of using C.
Right.
They're doing list C, list sub, or then list column, whatever.
Right.
So does it make more sense to use a for loop if you're kind of appending things to a list, if you know how long that list is going to be, instead of using one of these?
Well, you still wouldn't want to be appending. You would want to be filling in an already allocated.
Appending, like,
Okay.
so to speak.
So you're saying a for loop to iterate through and fill in chunks.
Basically, yeah.
Yeah,
Like that,
I mean-
that would be better than using apply in some cases if you're.
Well, yeah. So let me be clear here. It sounds like doesn't Barack Obama say that all the time? I just had that ring in my ear. Let's be clear here. What I'm contrasting here is a vectorized calculation, which is you take a function, you pass a vector, and you get a vector out with a for loop. If you're using apply, that's yet another mode of functionality. And often an apply is not going to be as fast as a for loop. It's sort of more elegant code in a lot of cases, but it's not necessarily faster.
So it's not always like.
So what I'm really contrasting is if you can do vectorized calculations, do them. Otherwise, if you need to use an apply or a for loop, then okay, you need to use it. And in that case, there's not always a clearly obvious winner between using some kind of apply versus a for loop. Sometimes the apply will be better. Sometimes if you're literally using apply, that's often going to be better than the for loop, although not always. If you're using lapply or sapply, that's not necessarily going to get it better than a for loop.
And I guess, sorry, as a short extension of that, as far as good programming practice in R, is there a general community consensus on that, or is it again kind of a mixed bag of, well, it depends on what you're trying to do?
Yeah, I would say the general consensus is vectorized is best, then using apply and lapply and sapply is good, not necessarily because it's fast, although some people I think mistakenly think it's faster than a for loop in all cases, but because it often makes for cleaner code, where instead of having a for loop and all the squiggly brackets and having to iterate, write out the iterating index and everything, you just often it's just a one-liner of you do an sapply with a function to a list. So it's somewhat more, I think, code clarity than maybe explicitly speed. Okay, so let's move on and see some other examples of just this mode of what I was saying last time about let's try and think about different ways of doing things, brainstorm different things, and then test them out and just act empirically to try and see what works and what doesn't work. And in some cases, it's not going to be worth doing this because the extra speed gain is not all that much, and sometimes when you try and do too much to try and make your code faster, code just becomes really hard to read. So as an example of this, let's look at 3 different ways of taking a vector and basically truncating any values in there that are less than 0 to be 0. So one way to do that is this if-else statement. Take this, and if any element that's bigger than 0, return the element x. Any element that's less than, return 0. Okay. Another way of doing this is to take the original x, make a new copy of it, and then say for any of the elements less than 0, put in zeros. Okay, so this is doing it sort of by indexing and Boolean logic. And then this is to actually do it in sort of a mathematical way, via a sort of purely vectorized calculation. So you'll notice that this if-else statement turns out to be quite a bit slower than either of these other 2 statements. And this last one which in some ways might be the most opaque of the sort of the most hard to read of them, is actually a lot faster than this one and somewhat faster, 3 times faster than this one. So what I want you to do is take a second and look at this, see if you can figure out exactly what's going on here and why that does the same thing as the other 2 lines of code. And then I'm also going to throw up, if I can do it here, the code for if-else and see if you guys can see why it is that that is so slow. So let's see if I can get all this on the same screen. Okay, so those are the 3 contrasting ways of doing it. And here's the if-else. Those of you who have your computer, it'll be a little bit easier to see. Let me see if I can get it all here. Okay, so there are the 3 ways of doing it. Here's if-else, so see if you can get a sense for why the if-else is slow, and make sure you understand what's going on here, and then we'll reconvene in 30 seconds or a minute or so. All right, so let's see. So first off, let's look at this line of code here. So I'm going to turn to my panel. So I think it's Danyi. Can you tell me what's going on with that line of code?
So the trunk x is x times x greater than 0. That one, right?
Yep.
Oh, okay. So we first, I think we first evaluate the thing in the parentheses.
So what does that give us?
It gives us x because
It gives us x. Well, it doesn't give us x. It gives us.
x greater than 0.
Well, x is a vector here. I guess maybe I didn't make that clear up here, but we're taking x to be just a vector of random numbers.
Okay.
So if I say x bigger than 0, what am I going to get back?
True.
Okay. Well, a vector of booleans, right? 1 for each of the x's. So I'm going to get a whole vector of booleans, 1 for each x. And then what happens? What must happen when I try and multiply that by x?
Get another vector of booleans?
Well, okay. So something has to happen here because these are just going to be numbers and these are booleans. So the question is, what sort of coercion must be going on here? So either one of them either they both have to be booleans or they both have to be numbers. Right? Okay. So in this case, what's going to happen is it's trying to do multiplication, so it's going to turn the booleans into zeros and ones, right? Okay. So then it's multiplying vectors of zeros and ones by the vector of x's. Anything that gets a 0 is just basically zeroing out the number, so it becomes a 0. Right? So that's basically just translating this if-else statement into sort of a mathematical way of doing the expression. And there oftentimes this will come up. Like I've often used this trick of like, I need to do this. I wonder if I can sort of turn that into a mathematical expression and do that in a vectorized way, or do that via a matrix calculation. We'll see some more examples of that. And so in this case, that's actually quite. We saw with the timing that's actually quite effective, and even more effective than doing this, where we're basically subsetting trunk x by a set of trues and falses, and then only assigning 0 into some of those. I wouldn't have necessarily known off the top of my head that this was going to be slower than this one without trying it out. I would have known, however, this one because I've seen this before. So let's turn to that. So did anybody notice anything about this? And I'm sort of asking at sort of a fairly high level here, if anything jumps out at you here of this. Yeah, go on. It's a lot of code. Okay, so that is one thing to notice here. Another question is what I'm sort of fishing for an answer here, obviously, but what doesn't happen in this code that we've seen in some other code? So there's no call to any C or Fortran code that's explicit in here. There's no .call, there's no .internal, there's no .primitive. So it's basically interpreting all this as R code whenever it does the if-else, and it's not basically sending it off to C. Any one of these lines is getting sent off to C at the sort of underlying level of how R executes any statement. But R is basically having to run through and interpret all of this code to do the evaluation. And so that, I think, is why this is fairly slow to do it as an if-else statement. So usually it's a good idea to use R's built-in functions. Occasionally there's a surprise where a built-in function like if-else in this case is actually much slower than we might expect it to be, and compared to some other ways of doing this operation. Any other comments or questions here? Okay. All right. There are a few suggestions here about sort of tips, some more tips for how to think about arranging data in rows and columns, and making use of the fact that we know that R stores matrices column major, so it's basically storing the first column, and then the next block in memory is the second column and the third column, and so on and so forth. I don't think I want to say too much more about that. Let's look at another example here, sort of skipping along and just trying to talk through some interesting examples. Here is another example of basically trying to use R's vectorized expressions and some built-in functions to do something in a fast way. So, so take a look at this line of code and see if you can figure out, I have some words up here that I think probably just say what it's doing, but see if you can sort of make sense of that line of code and see why, try and figure out why it is that in order to do this, which is basically subtracting off column means from each column, why it is that I need to do all this transposing and do the two transposes here. Yeah, X is a matrix. Thanks. Yeah, I should be better about setting these up so you have the necessary preconditions. Okay, so this is the sort of thing that we might use in a regression problem. We might want to basically standardize each column so that it's zero-centered, and we've subtracted off the mean of each of the columns in our design matrix for regression, for example. That's one case where it would come up. So anybody want to jump in with why I needed to do all this business with the transposing and why this then works if I do it with the transposing? Yeah, Alex.
So column means it's going to return vector,
Yep.
length dimension of your matrix. And then when you do the subtraction, it's going to subtract from the rows, but you really want the first entry of column means to be subtracted from the first column.
Yeah. So what's going to happen is suppose I sort of abstract away from this about the business of the column means phone. If I take a matrix and subtract a vector from it, what's going to happen is this vector is going to be subtracted from each of the columns of the matrix. So can anybody give me a reason for why that is the default way that R does things? So how does R store matrices? Stores them by column. So R, sort of the default answer to any question that I ask you like that is going to be, oh, because R is column major, right? So if R stores matrices like this, then it sort of makes sense that if you subtract a vector from a matrix, R wants to treat the columns as sort of the units of the operation as opposed to the rows. So therefore, by default, any vector that gets subtracted from a matrix is going to be this vector subtracted from this column, the same vector subtracted from this column, the same vector subtracted from this column, and so on and so forth. Okay. So if I wanted to subtract off the row means, I could have just said, okay, take the row means of this, and then do this minus row means of the row means, the resulting vector from row means, and that would work, because that would subtract off the first row mean from each element of the first row, the second row mean from each element of the second row, and so on and so forth. But because R is column major, and because for this particular problem I was interested in subtracting off the mean of each column from every element in a given column, I need to first transpose it so that it's amenable to doing it's amenable to doing the subtraction of the matrix minus the vector. Yeah.
So if your matrix is not square, does it give you an error, or does it automatically adjust to?
No, it'll still work. You can transpose a rectangular matrix that's not square.
No, so if you don't transpose,
If the
do
second
it the wrong way.
dimension isn't equal to the vector.
Yeah, does it?
Oh, I see. Yeah, no. Then you're gonna have a problem. R is then gonna do recycling, and it's basically, if you're trying to subtract a matrix where it has 10 rows, and you're subtracting a vector that has 8 elements from that, it's going to fill in the ninth and the 10th element to be the first and the second element of the vector. Yeah.
Doesn't give you an error?
It'll give you a warning. It won't give you an error. So yeah, lots of people don't like that about R, that it does that recycling. In some cases, it's handy. But yeah, so that would be an error, and we'd actually like it to return error in that case, because that indicates that we haven't actually figured out, do we actually want the row means or the column means, and we haven't gotten that right in our code. So actually, this way of basically, it's called, another way of talking about this is called sweeping out the column means. You can also do it. There's a sweep function that would do it, and it's interesting to see that the sweep function is actually rather slower than doing it this way, where we actually do a transpose, subtract off a vector, and then transpose back to get it back to the original orientation. So sort of interesting if you like this sort of stuff. Okay. Let's now turn to another example. And here I'm going to give an example of where I turn an operation into basically doing some linear algebra. Not complicated linear algebra, but doing some linear algebra. So suppose we needed to find the sum of each row of a matrix. Okay. So here I'm going to throw out 3 ways of doing that, and I'm using benchmark to time them. And here the code's a little bit hard to read just because it's not spaced out very nicely, but you can see down here much more easily. So we actually have the built-in row sums function, which we can apply to a matrix to get the sum of each row. Or I can use an apply, right? So every row of this matrix, apply the sum function to that row, and that will give us an answer. But it occurred to me at some point or another when I was putting a lot of effort in trying to make some code go faster, and I think maybe this was before row sums existed or I didn't know about it. I was like, I could actually figure out the row sums by taking the matrix and doing a matrix vector multiply by a column of ones, a vector of ones, and that will also compute the sum, right? I've got a matrix, a vector of ones. If I multiply this vector by the first row, that's just doing 1 times each one and summing it up. So that is the same as doing the sum of the row. And so I could actually represent this just as a linear algebra operation with R's linear algebra matrix multiplication operator. And it turns out that's actually a little bit faster than doing an apply, not a great deal faster. But it turns out in this case row sums beats it by a good bit. It'd be interesting to know what algorithm this is using, because this is actually sort of shockingly fast compared to the others. And usually linear algebra is fairly fast because it just goes directly to calling the built-in linear algebra routines that are on the computer that are already compiled code. Okay, any questions about that? Okay, so the next problem I want to pose to you guys is this one. If you have the underlying unit 6-rprog.r code file in front of you, don't look at it because the answer's in there. So the point is to try and think through this and see what we can come up with. So here's the question. Suppose that I want to take a matrix and I want to take successive differences of the columns. So I want to take this matrix and I want to get out, after applying some function to it, I want to get out as the first column the difference between the second column minus the first column. And then, so this will be 2 minus 1. And then the next thing I want to do is take the third column minus the second column. And so on and so forth, up until I get to the nth column minus the n minus 1 column. So the question is, how could I do this? So try and think of different ways that I might do that. And the second question is, try and think of how I could do that as a matrix algebra operation. How can I set up? How can I set this up so that I can do some matrix algebra where I take this, do some matrix algebra to it, and produce the resulting matrix of interest. So take a minute or two, try and brainstorm. Feel free to chat with your neighbors, and then we'll see what people came up with, and then we'll time out some of the different possibilities. For simplicity, feel free to treat the matrix as being square, although I don't think it's going to matter too much for the purposes here.
Mine's 256 kilobytes, like this I got. Yeah. Which makes a big difference.
How would you do it?
You minimize by like block the matrix such that they block in matrix.
So basically,
Yeah. And those you can work with like right there in your dash.
All right. So what have people come up with? Aurelia?
So I have the solution for the matrix.
Can you speak up? I can't
I
hear.
have the solution for the matrix.
Okay.
So what we do is we multiply the matrix, the matrix. We multiply it by the matrix with -1 on the diagonal and 1 on the subdiagonal.
Okay.
1.
So yeah. So what should that? So we're taking our original matrix. Which did I call it anything? No. Okay. So here's our original matrix. Suppose we call that X. And then where do you want me to put the ones and the minus ones?
So the matrix by which we multiply x, so the matrix on the right, we put some -1s on the diagonal.
Yep.
And 1s below
The subdiagonal.
Yeah.
Okay. Yep. And then 0 is everywhere else?
Yeah.
Okay. So everything else is a 0. So people see why that would work? Okay. So we've got this is one. This has a bunch of zeros in it. So this is basically saying, okay, -1 times the first element and 1 times the second element, and then the same thing. So we're basically, this operation of multiplying by this column is basically taking the difference of the first two rows and so on and so forth with these other ones. Okay. So that would be, so that's one solution, is to, this would turn it into the matrix multiplication thing that I was referring to here. Other ways that people can think of doing this? That's actually going to turn out not to be the best way to do it.
can you just like make a copy and then strip the first row and then add something to the end and then move it and then just subtract it?
Okay, so you want to do it as basically a direct subtraction of the two matrices, except we have to monkey around with the beginning and the end column. Yeah, so that would also work. So you're basically saying we want to take basically, what is it, the second through the nth column, that subset of the matrix, minus the same matrix, but where we have the first through the n minus 1th column of the matrix. Can anyone tell me a fast way to get this? Or at least, I think it's fast, but at the very least, a way where you would have to write very little code to do it? Yeah.
can use like the indices of the matrix. You
Yep.
write you want the matrix, let's call it A, bracket, bracket 2, semicolon.
Yep. So you can do
And
that.
it's,
Is that what you meant?
Yeah.
Or you could actually even do, anybody else see what I'm thinking of? What you could just, yeah, you can just do -1 to get it as well. So that'll say everything except the first column. So I could write this as x of -1, comma -1, minus x of comma minus n. So if we're thinking about analyzing, we could think about this theoretically, not very theoretically, but we can think about it sort of from a principled approach of, we're going to time these in a second, but you can think about how many operations it would take to do this, leaving aside the bit about whether we have to do some copying and as the process of getting rid of the columns. So if we just think about subtracting these two matrices, you can think about how many arithmetic operations that takes. It's just going to be, you're going to have to do one subtraction for every element of the matrix. So it's basically going to be n squared calculations. Not quite, because we're removing a column, but more or less it's going to be n squared. If we do this, anybody know offhand how many operations that's going to be? Do that multiplication? Yeah, so it's order n cubed. We're going to talk a lot about this when we get to the linear algebra unit. But when I multiply this column times this row, that's n different multiplications. Let's leave aside the additions for reasons that we'll talk about in a few weeks. So this is n different multiplications. Every time I do this with the first column, that's n different rows. So that's already n squared just from doing this matrix times this column. And then there are n columns, so I'm going to have to multiply another factor of n. So this is an order of n cubed operation. Yeah, Chris?
Is there any like sparse matrix that might help out?
Yep, that's where I was about to go, which is the other thing, if you're doing something like this and you're starting to think, you're coding this up and you're like, huh, there are a lot of zeros in here. Anytime you multiply by 0, that's basically a wasted calculation because you know exactly what the answer is before you do the calculation, right? So there are sparse matrix routines. There are some built into R, the capital M matrix package, the SPAN package. There are others built in. There's lots of other packages that do this. So if we were able to convert this to a sparse matrix format and then do the multiplication of the dense matrix times the sparse matrix, that would speed this up quite a bit. Yeah, Eugene?
So I know R can pull underlying like class libraries.
Yeah, it does, yeah.
Is it smart to recognize what kind of matrix you're calling it on?
It's not smart enough to do it unless you go through one of these additional packages and you tell it that this should be treated as a sparse matrix. It's not going to just look at it and say, hey, you've got a bunch of zeros. But it's not hard to do, so it's certainly something that you can implement. So I suppose the other possibility would be you could write a for loop that would loop through the columns and do the subtraction, and that would be another possibility. Did anybody come up with anything else, actually? There might very well be other things. So I think those are the ones that I put into the code in the R file. So if we actually look at this, what we should see is basically sort of what we just talked through in terms of the sort of the theory behind it. Okay, so here we go. I created a matrix 500 by 500, just filled it with random numbers, random normals. This bit here is just basically implementing what Aurélien was saying about filling in ones and minuses ones this fills them in on the diagonal, this fills things in on the subdiagonal. You could look at that code on your own in a little bit more detail and see if that works. And then we actually do the matrix multiplied by this new matrix A, which is this differencing matrix that we just talked through. And so you'll note there's nothing in here about sparse computation. So this is just treating it as full dense matrix multiply. So that takes about 0.3 seconds. This is doing it as a for loop. Actually only takes 0.037 seconds, so it turns out the fact that we're doing all this extra calculation with the zeros really does make a difference here. And then let's just try it as directly, just doing the direct subtraction of the matrices after pulling out the relevant columns. And notice that's even faster than the for loop, although not all that much. Well, I guess it sort of depends on whether we're thinking in absolute or relative terms. It is, it's more than 3 times faster to do it just as the direct subtraction of the two matrices. Okay, any questions or comments? Okay, so let me turn to, this sort of builds on this question of how many calculations do you have to do when you do matrix algebra calculations. So suppose I need to do this calculation. I have a matrix A, it's 5,000 by 5,000. Matrix B, it's the same size. I have a vector X, it's a length 5,000. I have to do the matrix multiply of A times B, and then I'm doing a matrix vector multiply here. So there are two ways that I could do this calculation. I could either first do the matrix multiply and then do the matrix vector multiply, or I could first do the matrix vector multiply and then multiply the result by the matrix. So which is going to be faster? Second one. Why?
Because you're doing two, like, it's like or a matrix vector, you're doing that twice. But for the first one, it's matrix and matrix, and that's a lot. So.
Yep. So if I do the grouping like this is matrix multiply. We just decided that if we have a square matrix, that's going to be order of n cubed. So if the matrices are all n by n, it's going to be n to the power 3 calculations. So this would be n cubed calculations, and then the result of that is a matrix that gets multiplied by a vector. That's going to be n squared calculations. So if I do it in this order, just from left to right, it's n cubed plus n squared calculations. If instead I explicitly tell R, and R is not going to be, I don't think R is, I'm pretty sure it's not going to be smart enough to figure out what order to do it in. So I'd have to explicitly tell it, I'd have to explicitly put in parentheses and say, do that first. But if I do this first, that's n squared calculations. The result is a vector, not a matrix. And now I take this, which is vector, and multiply by that, another n squared calculations. So it's the difference between doing n cubed plus n squared and doing 2n squared. And if you've got a big N, there's going to be a big difference in doing that. So even just simple things like the order of operations can matter when we're thinking about efficiency. Here's an interesting one that you can think about. If I need to find the trace of a matrix if the trace of a matrix where that matrix is produced by multiplying two matrices together, how could I do that in a fast way? And I can actually do it with the direct product of the matrices as opposed to actually matrix multiplying the matrices, but I'll leave that for you guys to think about. And there's another challenge in here of sort of working with diagonal matrices that builds on some of these same things that we've been talking about. Okay, I do have a couple comments here at the end of this, sort of building on what Chris brought up about and what Eugene was asking about in terms of sparse matrix calculations, and here are some references on that. Okay, so I want to say a little bit about sort of lookups and basically mapping between objects, between one object and another object. So the context that this might come up in, although it comes up in lots of contexts, is suppose I have a bunch of observations and they're grouped into different strata or different groups. And so I might have an ANOVA type model, so I have a bunch of y's indexed by I and j, observations I within group j. And each of the observations in group J shares a common mean mu sub j. And then, just for simplicity, I'm just assuming a single variance here. But if we're working with problems like this, there are going to be lots of cases where we need to say, okay, I have my vector of y's. I need to basically get the associated mu that goes with each of the y's. Or I might need to do something like take the mean of all the y's within each of the groups. Okay. So you can do things like if you need to get the means associated with each of the observations, you can do things like if you have a vector of the means, and if you have an ID vector that for each observation says which group it falls in, then you can just do some indexing like this. And that, let's suppose the mean vector is, say, 10 long and the observation vector is 1,000,000 long. This is going to go and basically create a vector that's 1,000,000 long, one for each of the IDs, where it's pulled out the appropriate mean for that observation. And if we want to go in the other direction, we can use the split function and then use something like an S-apply, for example, to compute a mean for across each of the groups. So if you know how to do this, you might, if you first saw this problem, you might okay, I have to write a for loop, I have to do all this stuff. But in this, for lots of these kinds of problems, there are very quick ways to do this with the facilities of the language. The other thing I want to point out is that R allows you to look up things basically by label or by name. So if I had a vector, say, of numbers that I'm just calling vals here, and suppose each of those I had given a name to each element of the vector. Let me actually switch over to R just to see what this looks like. Okay, so we've got this. Now I've got this vector, vector vals. You can see there's a label associated with each of the numbers. So this is still just a standard R vector, but it's got an attribute, which is the names. Just like a list can be named, just like columns can be named, or rows can be named in a matrix, we can name the elements of a vector as well. And I can, for example, pull out by label, by name, certain elements of this vector of values. So suppose I wanted to pull out, for whatever my particular operation was, suppose I wanted to pull out the H, another 2 copies of the H and the A and the C ones. I can do that by just explicitly passing in those labels or names, and that will indeed pull out the 4 elements of the numeric vector that I'm looking for. So that can actually be quite handy in terms of code clarity, because you can sort of see immediately what's going on. If these were more informative labels than they are here, it's really easy to see what's going on here. I'm selecting by name those particular values and so on and so forth. But part of the reason I wanted to point this out was just because A, it actually is quite handy, but also to think about efficiency here. So what I'm going to do here is a little experiment where I have a million values in a vector x, and I'm going to create a list out of that as well. So I'm going to have x and xl, which are the vector form and the list form of this set of numbers. And I'm going to assign names to the vector and vector elements and names to the list elements. And then what I'm going to do is I'm going to time how long it takes to pull out an individual element from either the vector or the list. But here I'm either going to pull it out by numeric index, or in this case I've just made the names be just the character string representations of the numbers. Or I'm going to pull it out by actually giving the name of the element that I want to pull out. And I'm going to do that either both in the vector and in the list form. So if we do this, we'll see there's a fair amount of difference in how fast this takes. And so this both gives us an idea of how fast is it to look things up in a list and how fast is it to look things up in a vector, but also how fast is it to look up by name versus looking up by index value. So let's say I go ahead and do that. Inconveniently not getting to the end here. Oops. Okay, so here's what we find when we look at the benchmarking results. Is that if I'm looking up by name, by character string in the vector, it actually takes a long time to do that. Right? I'm actually only looking up a single element here, so this turns out to be pretty inefficient. If I look up by index value, it essentially takes no time at all. And that's true in both the vector and in the list, although it looks like it's somewhat longer in the list. And then if I look up by name in the list, it's actually better than looking up by name in the vector, but still actually slow compared to looking up by index. So can anybody have any hypotheses about why it takes a long time to look up by name as opposed to looking up by index value? Yeah, so let's sort of translate that into a pictorial representation. And I'll do it for the vector because that's sort of simple to think about. If we have this vector x, we've already talked about the idea that that's stored contiguously in memory, and R knows where the start of that block of memory is, and it knows how long the block of memory is. And so what happens when we say to R, oh, go find the 500,000th element here, is it can basically just leap immediately to the 500,000th element because it knows how long this is and it can go there immediately. Well, now let's think about what these can be arbitrary names. I happen to name them quote 1, quote 2, whatever, but this could be whatever, Sam and Fong and Bill and Sarah and whatever else, whatever other character strings we want to put in here. And so okay, so we get down here, and this one is the one we're looking for. And okay, so what does it have to do to know to go here? It has to go and say, okay, what's the name of the first one? Is that the one I'm looking for? No. Is this what I'm looking for? No. Is this what I'm looking for? No. Is this what I'm looking for? No. So it basically has to do all that querying until it gets to this one, and that's going to take a lot of time to do. there's probably somewhat different stuff going on with the list in terms of the lookup because it's so much different. It'd be interesting to delve into that. I don't know exactly off the top of my head why that is. And lists have to be stored somewhat differently because lists can be composed of arbitrary elements. So there's a lot of more complicated stuff going on with the memory management than just with the vector, where there's just each element is the same length. All right, let me see what else I want to comment on here. All right, so I have a little bit to say about hashing, but I don't think I have enough time to do that. So let me make a few more comments, and then I'll come back to hashing next time. There have been some efforts in the last 5 or so years to basically make faster versions of R and to improve the speed of certain operations in R, because R is fairly slow, at least if you do things in a naive way compared to other languages. And a couple of those are so basically there's this idea that R is a language, but you could actually have a different way. You could actually have different programs that take code that you write as R and interpret the code and do the calculations. And so the idea is there's sort of an engine behind the scenes that's interpreting the R code and running the operations that you've specified with your R code. But there's no reason that you have to use the R engine that's provided by CRAN. You could use another R engine that interprets the language and then gives you back the output. And so there have actually been some efforts in the last few years to basically create other back-end engines for R. I didn't actually mention all of them here, but one of them that's been pretty interesting is something called PQR, which stands for Pretty Quick R, which is kind of cute. And it's by this guy, Radford Neal, who's a statistician and computer scientist at the University of Toronto, who's pretty well known in the computational stats community. And he's done a bunch of work to basically avoid making extra copies of objects in R, which is something we're going to talk about. R already doesn't make copies in some cases where you might expect it to make copies, but he's done a bunch of work to avoid even more copies. And I think some of that is now being built into more recent versions of R. There's also a lot that goes on if you look at some of the functions in R that would do, for example, matrix calculations. What you'll often see is sort of a block of R code, and then it'll call a C function. And that block of R code is often just sort of going through and checking, is this a matrix that's numeric? Is this a square matrix if I'm going to then do something that needs a square matrix? Are there any NAs in this matrix? And all of those checks take some time. And in some cases, often that's useful to have those checks so that things don't go wrong. But in some cases, you don't actually need all of the checks. And so he's made some efforts to avoid some of those checks. And another example of what he's done that tries to avoid inefficiency is when R does this or this, something actually fairly stupid happens, which is, what does this mean? It means iterate over the numbers from 1 up to n. But R literally, when it sees this, expands this out and creates a vector, 1, 2, 3, 4, 5, up through n. And then it iterates through that vector. Well, there's no reason that R needs to actually create that vector. You could just take this code and basically translate that as iterate through these numbers, 1 up through n, and never actually create the vector. So that's another example of sort of inefficiency that is built into sort of the standard R, but there are ways around it if you write an interpreter that doesn't actually expand this out before it evaluates the for statement. And similarly for sort of like subsetting from a vector in this sort of way. So we actually have this PQR on the SCF system for those of you with SCF accounts, and it's actually, I think it's fairly easy to install regardless. One drawback is this is based on R 2.15, which is a fairly old version of R, so then you have all sorts of problems with if you install this. The packages that you need that are for R 3.0 or 3.1 don't work with 2.15, or the packages for this don't work with the current R. So there are some hassles, but it is interesting to check out if you're interested in this sort of thing. Okay, so I'll close there. I'll say a little bit about hashing next time, and then we'll turn to talking about functions and memory use on Monday. And do look at my announcement about section on Monday and do the reading that I asked you to do in advance for section on Monday. And if anybody was not here on Wednesday and wants to pick up a copy of the Solutions Problem Set 2, there are few extra copies up here.